All right. Please make anxious-looking faces if the slides are not matching up with what I'm speaking. All right, so for the last few years, my collaborators and students and I have been working on building sort of state-of-the-art Datalog engines and trying to figure out, primarily for the purposes of things like program analysis, but also social media mining and graph mining applications, that sort of things. So what is Datalog? Datalog is a sort of reduced logic programming language. It's essentially just positive horn clauses over atomic literals. There can be negative variables, or negative predicates, but only if they can be stratified. So we'll just focus on this small fragment for now. So here are two example rules. So the first one says that when there's an edge between x and y, there's also a path between x and y. The second rule says whenever there's a path between x and y, and there's an edge from y to z, then there's a path between x and z. And so Datalog is an extension of SQL to handle recursive predicates and recursive rules. So the first rule is just plain old SQL. So here you can imagine that we're setting path to be everything from edge and basically saying copy everything from edge into path. Now the second rule is sort of a recursive or inductive rule. And we can't write this using SQL. Well, we kind of can if we use some extensions, but those extensions are not really going to be good for our purposes. They're a little bit too slow. SQL engines aren't really made to handle these kinds of heavily recursive queries. That's what Datalog is for. So the second rule is going to be evaluated in a fixed point loop. And the idea is that every iteration of the loop, we're going to join path and edge. We're going to get some new sort of transitive paths, and we're going to join those into path as well. So the first iteration, for example, will give us the 2-hop edges, and then 3-hop edges, and 4-hop edges, and then eventually we'll hit a fixed point just because the sort of graph number of possible edges between things and transitive edges is finite. But of course, if we remember our sort of high school abstract interpretation class, you can remember that if we sort of rediscover edges a whole bunch, then that's going to lead us to do asymptotically more work. And so the thing that I just talked about is called the naive evaluation strategy. And of course, we don't want to be naive. We want to only be semi-naïve. And so the fix is that we compute basically these delta relations, or something like a frontier semantics, so that path delta is tracking all the edges discovered in the most recent iteration. And so the idea sort of here in Keynote is that you take all of the things that, basically you take the black edges, you turn up their opacity, and then you take this delta relation, and then you do only this join, but you ignore all of the stuff that's opaque, the orange stuff that's not from the previous generations. And of course you get some more transitive edges and keep doing that until you reach a fixed point. All right, so if Datalog is just this relatively simple horn-sat kind of sort of logic, not even nearly Prolog, for example, nothing like the cut, no backtracking, anything like that. Why does anybody care about it? Why is it useful? Oops. So the observation is that actually this kind of forward reachability at extremely high scale, which Datalog is really good at for some reasons that I'll talk about later, is very useful for a bunch of different examples. So for example, program analysis, the top program analysis engines in the world right now, at least of a certain style, are written using Datalog engines. And so you can get orders of magnitude less code compared to, for example, Walla or Soot or something like that. You can write them in several thousand lines just for a complete implementation of a whole analysis of, for example, Java. In the case of JUP, DDASASM is the most accurate, precise disassembler currently known, and CCLizer is an analysis of LLVM. You can also do things like graph and social media mining, so transitive closure, k-click, things like that. And also recursive aggregation, which is an extension of Datalog to put sort of reachability in a loop with an aggregation operation, so things like shortest path and PageRank and things like that. So Datalog's restrictions enable lots of modern implementations to leverage sort of several tricks that give us extreme speed. So the semi-naïve evaluation, indexing is also very important, parallelization, very key, and efficient tuple representations with respect to things like locking and space-efficient representation. And modern engines really need all of these to be performant. So the state of the art is nested loop joins with explicit representations. Previously, we tried to use BDDs back in the 90s and early 2000s. They had variable ordering issues. Then we've kind of found that more recently, these explicit representations with good optimal indexing works very well. So what's the catch? Seems like it works really great in many circumstances. But of course, Reynolds tells us that whenever you implement something in a language, you inherit that language's features. And so the data structures that the engine provides, if you're implementing an analysis or something, some kind of analytics in the engine, the data structures can be leaky abstractions when there's an impedance mismatch between what the engine provides and what you need to use. So for example, let's think about 2 clicks and this transitive closure case. Well, unfortunately, we end up with something like this. And so, if this is not what you want, maybe not so good. But it's not just these graph operations. A similar extension of the little picture I just showed shows us why we can't do Steensgaard-style analyses in Datalog either. So some modern engines try to assuage this by offering us a sort of fixed set of data structures that we can choose from. But of course, that only goes so far. If you're not an author of the engine, then you have to expend a whole bunch of time figuring out how to extend the engine. I've spent a good amount of time trying to figure out how to extend Soufflé, but I don't like C++ much myself. So we present a new approach called bring your own data structures. In Byods, you can write something like this. So you specify that we want to use the transitive union-free relations, and that will make sure that this turns into this. And this TRL UF is backed by a union-find-based data structure for transitive relations. So Byods is a macro-based Rust-embedded DSL that compiles to Datalog to efficient kernels, which hook into user-provided data structures via an object protocol, realized programmatically via Rust traits. We have a formalism called DL sub DS, core formalism for harmonizing user-provided data structures with Datalog. And these are defined by something that's basically not quite Galois connection. There's not the round-tripping property required. This is important for some reasons we explain in the paper. So D has to be a lattice, and there's an injection function and a concretization function, and then you can define the naive semantics in terms of those, and everything kind of works out. And the theorem says that if all the concretization functions are monotonic, then so is the immediate consequence operator for the program as a whole. We give more details in the paper. It's one of those interruptions. Including a semi-naïve semantics as well, which says sort of a characterization of what is required for these data structures. So we define this via a 2-stage protocol. The first is compile time, where macros specify sort of this formalization. So for example, the user has to specify rel ind macro, which computes the type of logical indices. This is called by the Byods compiler to figure out indices as the compilation happens. Rel int common computes the carrier type that's actually going to represent these tuples. So for example, if I define a relation, this little hash and then ds my provider says use the my provider sort of representation. I'm defining this relation foo with 2 columns. And then Byods will invoke the data structure's rel int common macro, which will then cook up a representation for the carrier type. And the data structure providers can use arbitrarily complex logic to construct types for relations and indices. For example, we implement Soufflé's optimal index selection, which is a major pass in innovation in the Soufflé engine that we were able to implement just in our library in Rust. The second stage is runtime. So relation backing data structures have to implement 4 Rust traits. Rel index read, which reads from an index. Rel index read all, which iterates over a relation. Write, which writes to an index. Rel index merge, which does semi-naïve evaluation or merges things in at the end of the loop. We built Byods to be an extension of Ascent, which is a previous Datalog engine that we built in Rust. It did not have parallelization, it was just serial, worked with kind of a traditional strategy. It implements a fully featured state-of-the-art Datalog that's competitive with Soufflé and all the other engines that you sort of probably know and love, including parallelization using Rust's Rayon and work stealing. And we observe performance on par with Soufflé Frankly, I think it's better than Soufflé, although I can't claim that it's universally better. Soufflé has lots of good innovations. For example, Soufflé has feedback-directed join planning, and they've done a lot of innovation in that space, which we haven't done. We'd like to integrate that into Byods someday. So let me show some results. So we re-implemented Polonius, which is an implementation of the Rust borrow checker currently being implemented by the Rust working group and trying to be used in the Rust compiler. I think maybe it even is right now. We've implemented this in Byods. And we compared using explicit versus transitive relations versus index sharing. Transitive relations give us a 2x speedup and a 1.5 to 2x compaction in memory. This is single-threaded. The way that Polonius is written, there's not very much parallelism to exploit. So we tried running it in parallel. It didn't really help. And everything runs pretty fast, at least in these experiments. Index sharing means more write contention, so it's going to be more compact, but you're going to be sort of writing across things. Not such a big deal here, but we're going to see it more later. So we tried doing transitive closure via union find, so the catastrophic picture I showed earlier. We see time improvements of up to 10x and memory improvements of up to 30x, and of course this is going to depend on the dynamics of the graph. If you have a graph that's very sparse, has very few clicks, then this isn't going to help you very much. We get extremely good parallel results. This is not a direct property of Byods itself, but it's more just evidence that Byods can sort of integrate with high-performance modern implementations. My experience is that Soufflé scales to roughly 4 to 8 threads because of the way the data structures are designed. Byods uses Rayon's work stealing, and we're able to see very nice performance. This is a 32-core, 64-thread server, and the thing I think is really exciting about this experiment, PageRank, which shows an extension. It's not just sort of Hornsat reachability, it's also lattices, because you need to be able to do monotonic updating. So the thing that I think is really exciting here is that the bigger the problem gets, the more parallelism there is to extract. So you can see at 64 threads, we get a roughly 40x speedup on the largest graph with, let's see, 4.3 million nodes. And last, we paired with some of our partners at Galois, and we have used Byods to implement one of the, at least in my mind, very robust sound analyses of LLVM. So it's a 2.5 thousand line, roughly, analysis of LLVM in a combination of Byods and Rust. The thing that's really exciting to me here is that it's really written the way that you would actually want to write the analysis. You don't have to do a whole bunch of massaging to throw things into Soufflé or some other engine. You can use the most popular LLVM parsing library in Rust and throw things directly into Byods without any extra work. Our analysis is an Anderson-style MCFA, so the M-top stack frames, and it follows the abstracting abstract machines approach. Comparable to CC-Lizer, CC-Lizer is not sound. It's designed to be more precise, but we found that the soundness or the lack of soundness is a serious issue in practice. But YAPAL is. And we also measure the impact of index sharing. The thing that's most exciting to me here is that using this approach, we can complete a one-context-sensitive analysis of HTTPD, enumerating 5.3 billion control flow points in 7.3 hours at 8 threads and 2.7 hours at 32 threads. If we use optimal index sharing, it cuts the memory in half, and it allows us to compute an analysis of HTTPD, which otherwise just blows up and doesn't terminate on our 512 gigabyte server. Now, the index sharing is not universally good. It does induce more write contention, because since you're sharing more, there's going to be more times where you're going to be waiting on trying to update a data structure. And so, for example, we can see over here on the sort of smaller program, Jackson, at 8 threads, we can see it's 8 seconds versus 10 for the default. Default is without index sharing, meaning there's more copies of things, but you've got worse sort of memory performance. But in Redis, for example, using index sharing, it's 19,000 seconds versus 11,000 seconds. So, yep. Okay. So thanks so much. The thing that we've tried to show here is that it's possible to get state-of-the-art Datalog performance as a library, but the engine's data structures become leaky abstractions. Instead, we propose bringing your own data structures. Ascent is now public. We've integrated the ideas from Byods into Ascent, and more of them are being backported, although there's also an artifact you can look at. YAPAL, the pointer analysis that I mentioned, is also open source and public, open sourced by Galois recently, and I would encourage you to take a look at that as well. And I'd like to end by saying that this is not primarily my work. I helped Arash do the writing. I'm his advisor, but primarily this is the work of my student, Arash Sahebolamri, who's now graduated and working in industry. So thanks so much.
Thanks for the great talk. What about negation? Can I write a data structure that uses negation inside? And can I use a data structure in a program that uses negation?
All the typical negation I'd love to. That's, you know, I have an NSF grant that we said we were going to do that in, so let's hope we can.
Okay. If in 3 years you haven't done it, I'm going to be on your neck.
Yeah, I'll have to report back to the government.
Have you discovered any data structures you cannot abstract by lattices, right?
Oh, that's a great question. Well, I guess I would say you're constrained that it has to be represented as a relation. So one thing I would say that I think is kind of not so great about this work is that there's some other really nice work out there called Egglog by Max Wilsey and folks. And they have a better story in terms of how joins get performed. We have to materialize whenever we perform a join, and there are some tricks that they can play. Those tricks don't generalize very well across different data structures, so our work is kind of, you know, more general, I guess, not just union find, but we don't get as good performance as Egglog in some specific cases asymptotically, although, you know, they don't support things like parallelization and, you know, Rust and things like that. Well, I guess, you know, yeah.
Is there time for another question? Or?
No.
No. Okay.
Sorry, let's thank the speaker again.